So good afternoon, everyone. I think we should start. So in the last lecture, we reviewed a few commonly used probability distributions, such as Bernoulli distribution for binary random variables, and categorical distributions for categorical variables, and beta distribution, Dirichlet distributions, which are used as the prior distribution as the parameters for Bernoulli distributions, or parameters for the categorical distributions. Then we'll look at the distributions for random for the continuous random variables. So most commonly used are Gaussian distribution and multivariate Gaussian distribution is our emphasis in the last lecture, and everybody should be familiar with how to derive the conditional multivariate Gaussian distribution. Like given one Gaussian random vector, what is the conditional distribution for the remaining Gaussian random vector, and then you can use this square completion tree to derive the marginal distribution for any subvector of your Gaussian random vector. And also we introduced what is T distribution, right? So T distribution is also referred to as the infinite mixture of the Gaussian distribution, because it can be expressed as an integral. The integrand is Gaussian and multiplying with the gamma distribution over the inverse variance of the Gaussian distribution. So that's why you can consider it as like a weighted summation, infinite weighted summation of the Gaussian distribution. And the property of the T distribution is the heavy tail, right? You mentioned that. And basically it assigns more probability mass on the tails of your of the density curves, right? If you use the original normal distribution, then on its tails, the density or the probability mass is quite small. But for T distribution, the mass is much larger. So the benefit is that when our data set contains some noises, T distribution will give you a more robust and reasonable estimation. If you use Gaussian distribution, you do the maximal electrical estimation. If there's some like noise which is far away from most of the data, then your Gaussian distribution will immediately becomes a very wide effect curve, right? But if you use T distribution, it can still keep its original form, which is much more reasonable. And also there is a multivariate T distribution. So I hope you'll be familiar with common use distributions, as we mentioned in the last lecture. Those are like basic components of probabilistic modeling, and you can use them as like basic traits or components to build out more complicated probabilistic models. And so today we'll start to look at some basic concepts in information theory, which are very important to probabilistic modeling and also machine learning. Of course, information theory is a huge topic. We're not able to cover many details. We'll just focus on several very important concepts. And then we'll introduce conjugate prior and exponential family, which takes the key role in the probabilistic inference. Because when we do the approximate inference, when the true posterior is tricky to compute, a commonly used strategy is to specify a family of easy distributions and pick up one from this easy distribution family to approximate the true posterior. Then what is the family? What is family for the approximate distributions? The commonly used family is called exponential family. So exponential family is a family of distribution which is very simple but quite flexible and has many nice properties. So let us start with the basic concepts in information theory, and we'll look at closing theory. So let us start to talk about discrete random variables. Suppose I have a discrete random variable. It's not continuous. A natural question would be, like, how can we come out a measure which can measure the information amount contains in this random variable, right? So first, you do not need to look at this part. Right? So let us first consider, right? If you are some golf, right? You want to design a measure that measure the information contained in a random variable. How do you design? Right? So first, naturally, I want the information, the measure of the information must be non-negative. Naturally, it's not very reasonable or intuitive to have a negative information. What does it mean? So basically, at first I want my information measure is non-negative. A second thing, second natural principle comes from, like, if I have two random variables, what's the relationship of the information measured on these two random variables with the information measured on each random variable? If x and y are independent, that means if you know x, you still know nothing about y. Right? If you know y, you still have know nothing about x. So naturally, I want my definition of the information on this x and y, when x and y are independent, to be the summation of the information of x plus summation of the information y. Does it make sense? Yeah, because x and y are independent, right? Basically, okay, x contains its own information, y contains its own information. There are no overlapping. So if I know x, I know nothing about y. If I know y, I know nothing about x. So naturally, if I define an information measure, that should be like their joint information should be the summation of their individual information. So these two basic principles. These are two basic principles, right? So now let us try to associate our information measure with the probability, because we use probability to describe the behaviors of those random variables. So now, first, when x and y are independent, so now their joint probability is the production between their individual probabilities, right? Px multiplying py. So now we say, okay, if they are independent, their joint probability satisfy this multiplicative structure, right? But in our information definition, we want to have this additive structure. How do we build that connection? Yeah, heard that. Take logarithm, right? If you take a logarithm, okay, you immediately turn the multiplication into the addition. So you have the same structure. But remember, we also want our information to be non-negative. I would not want our information to be negative. That's not intuitive. Then what should we do? The probabilities are less than 1, right? If you directly take logarithm of that, you get a negative value, right? But now I want my information measure is non-negative. What's the strategy? I heard that. Yeah, just take minus, right? You first take logarithm of that, and then you put minus on both sides, right? Then it comes from then you come up our definition of the information. to ask you to design a measure. So forget about your memories about like what is the entropy, what else, right? So I want you to define a function which can measure the information a random variable contains.
What's the goal of this design?
What's the goal of this design? There are a lot of goals, a lot of usage. Right? You have a random variables. Right? You know random variables can appear here and appear here. Obviously, there are some information associated. Right? But you want to study it, you must give quantitative analysis. Right? You must come out a function which can measure this. So if no teacher, no professor teach you what is information definition, can you come out a function to give such a measure?
I come on an example, have to satisfy these two
Properties.
Yeah.
Yeah. This is one choice.
One is like not negative. Why we should be able to add two independent information?
That's basically an understanding of your information. Right? So if you are asked to design something, like you are asked to design a car, I want to design a beautiful car. Right? So what kind of properties you want your car to satisfy? First thing you want your car to have wheels rather than the shape of the wheels should be circle, right? Rather than like rectangle. This is some kind of properties that can come out in your mind. And secondly, you want your car to say to burn oil rather than use other things to burn, right? So now I'm asking this because in machine learning, there are not often like every time you can pick up some measurement from some textbook, you are required to define something. Right? Suppose you want to measure somebody, it is knowledgeable or not. You want to come out a function to define that. So you need to first consider, before you are given some specific function form, you need to first consider what kind of properties your function can have, right? So first, I cannot define a function of a knowledgeable function to be negative. That's counterintuitive, right? What do you mean by negative knowledge? I can say, okay, somebody has no knowledge. His knowledge is empty. So it's zero, right? Or if someone has a lot of knowledge, is very comprehensive, then his knowledge function could be very large. I see, 100 or 10 to 6 or 1 million. Right?
So the measure kind of measure the amount of the information.
Yeah. Does it make sense? So now I'm the one who is responsible to define a measure which measures the amount of information that a given variable contains, right? And from the very beginning, before I come out any analytical form of my measure function, I want my measure function to be non-negative. And for any two independent random variables, I want the measure of their information contained jointly is equal to the information of x plus the information of y. Right? And then I associate these properties with the probability, because there's a rich theory about probability, right? And I found that connection. If I build that connection, I can take a logarithm, take negative, and then I can come out my first candidate function like this, right? And it satisfies these two properties. Obviously, you can come out whatever other functions you like to satisfy these properties as well. Or you can argue that actually I don't want this. I want other. It's fine. But now let us stick to this, right? So now based on this, okay, I know whenever when random variable x takes a specific value, I can design its the information it contains is just this one, negative logarithm p of x, but x is random. So I need to remove the randomness. So I take expectation. I take expectation over the random variable x, that is the summation over all the possible values the random variable x can take, weighted by the probability. So that's where the entropy comes from. You can think of, like, you can try to take the role of Shannon. So before Shannon, there's no definition about like entropy. Of course, this might be wrong. Right? There will be some kind of informal definition similar to the entropy. But suppose you do not know that, and before Shannon was born, right? You want to define a function and measure the information a random variable contains. How do you design it? Obviously, entropy is one design. Right? Of course, you can design other kind of measure. Depends on you. As long as your assumption, your requirements sound reasonable. Does it make sense? So let us look at the one example of entropy. So suppose our random variable x can take 8 values, right? 8 values, taking a value from A to H, and these are the probability masses 1 over 2, 1 over 4, 1 over 8. Right? We can calculate the entropy. According to the definition, you need to sum over all the possible values x can take, right? For each summand, you take negative logarithm of the probability and then weighted by the probability. That's just the definition of entropy. And here we take the base as 2 because we want to use 2 digits to code a random variable. That's only meaningful for like coding theory, and you want to design some code. But in our scenario, you can choose whatever base. And finally, you end up with 2. So from a coding theory, it just says, okay, entropy is average code length. You want to encode a random variable. And if you know the distribution of random variable, what is the most efficient way to code random variable? It's called Hoffman coding device, if I'm not wrong. So entropy is also a measure of the uncertainty. So basically, uncertainty is equal to the amount of information. So when people say, okay, this random variable contains a lot of information, it just means the uncertainty of this random variable is very large. Why? Because suppose that you don't have a random variable. Your variable is just a constant. So you know, in whatever case, your random variable just take one single value, so 3. So actually, the information contained in X is tiny. Because you know, in whatever situation, just X, right? The uncertainty of this random variable, constant, is 0 as well. Because you know that for sure. But if a random variable X can take a lot of values, right? And then you can say the information it contains might be much as well. Because you know nothing about, now you know nothing. You know the range it can vary can be much, right? In other words, the uncertainty about X is large. So basically, we can treat uncertainty as equal to the information it contains. the more uncertainty the random variable we have, the more information the random variable contains. So it is equal. Don't confuse. Don't confuse at this point. So basically, in this engineering or science disciplines, uncertainty equals to information contains. But it's not knowledge. If people think about it's knowledge, then you think, okay, I'm clear about everything about that, right? But it's not knowledge. It's just some information you do not know. Does it make sense? So, so if you calculate some example random variables, the entropy for some example random variables, you say if your the value of your random variables taken is kind of concentrated, like I know, okay, this discrete random variables has the largest chance to take it here and has almost zero chance to take it here. It is entropy, 1.77. Right? If your distribution, probability masses of the probability mass of your random variable is small y, okay, so it has not significantly different probability masses over the choices of different values. If you calculate the entropy of these random variables, underline this distribution, you get a much larger entropy, right? 3.0. So that means the larger, but from the distribution, you can also say intuitively this random variable is more uncertain than this, right? Because you can roughly estimate, okay, for this random variable, it just move around here, right? And more likely to appear in the center, right? But for this random variable, okay, it can jump quite far away. So of course, I'm more uncertain about this. And the entropy reflect this observation. So, does it make sense? So now let us consider, if I have a random variable, we have m possible spectrums. So that means the random variable can take m possible values. So represent this random variable as m by 1 hot encoding vector, right? So it could be 1, 0, or the others are 0, or 0, 1, whatever. Right? And the distribution of this x is controlled by a probability vector. So it's P1, P2, which Pn, right? So natural question would be, what kind of choices of this P1, P2 to Pn can lead to the largest uncertainty? In other words, what is the largest entropy? We're going to try to solve this problem. Then we may have a more, a deeper understanding about the entropy and how it is associated with the uncertainty. So let's try to solve this. So according to the definition, the entropy is defined like this, right? So for briefly, we can rewrite it as summation over I, pi, logarithm of pi, right? Pi is just the probability of x taking the ith value. And now, remember, because this is a probability vector, we also require that the summation of all the probability values to be 1. So to maximize entropy, we need to add this constraint. Then we use the range multiplier. So our objective now becomes, so I will write it again. This, first, the entropy term plus the Lagrange multiplier on this one, right? And this is for, we want to find the optimal P1 to Pn, right? So let us try to do that. to maximize this objective, we just take a derivative over each P1, P2 to Pm, right? So let us just take arbitrary, say Pj, right? The jth element in the parameter vector. So we need to calculate the partial of each tilde, which is the augmented entropy with the logarithmic multiplier for Pj. So what about partial derivative of the first one? Just use our basic derivatives, right? So let me put because it's summation over all the elements, right? So you just need to take the I sum. So it will be partial derivative over Pj, logarithm of Pj over Pj, right? Plus, and for this part, what is the partial derivative? It's not constant. There's a lambda, right? There's coefficient lambda. So it's a lambda. You must obtain this. You must set this to 0, right? So is it clear to everybody? If it's not clear, just let me know. So then you can calculate this one, right? So the partial derivative of this one, which is what? 1 plus, first you can focus on this term, right? So it's a logarithm of Pj plus, and then you will take derivative of this, so it's Pj over Pj plus lambda equals to 0, right? So now you can further get minus 1 plus lambda equals to 0. So if you just manipulate it, it is just exponential to minus 1. Do we need to further calculate?
I don't understand where the Lagrange multiplier came from, though. Back at the beginning.
Oh, because we need to ensure that the summation of P1, P2 until Pm must be 1. Does it make sense? Because you can only choose one status, right? You have say you have a P1 chance to take category 1, P2 chance to take category 2, right? You must ensure that all those chances adds up to 1. Any other question?
I couldn't understand that. Could you explain why the probability needs to add to 1, but then how does that bring up the
First, x is a random variable, right? So this is a categorical random variable. So the distribution, what is the distribution of categorical random variable? If you write down the probability mass of the random variable, is just the product over all the value it can take, right? This pi to the xi, right? And we must ensure the summation of all those pi to be 1, right? Like you can take 3 possible status, right? You have 1/3 chance to take status 1, 1/3 status 2, and 1/3 status 3. This is one example, right? You cannot like take 1/2, 1/2, 1/2, because the chance adds up to be over 1. Right? Does it make sense? Any question? This is just an example to show. Let me finish it. Let me finish the example. So from solving the partial derivative 0, we get that Pj, the jth element in this parameter vector, the probability vector, must be exponential of lambda minus 1. So what can we conclude from this? Yeah, because lambda, there are only one lambda value, right? So that means, and we see the value of Pg does not depend on G. So actually, that means P1 equals to P2 and equals to Pn equals to e to the power of lambda minus 1. Right? And we know that the summation of all the big N probabilities must be 1. Right? And what can we conclude? Each element must be 1 over N. Right? This is the result. Now let us look at that. We know when P1, P2 to Pn, they are the same, meaning that you have a uniform distribution. Your entropy becomes the maximum. What does it mean? It means the uniform distribution. If your random variable is distributed uniformly, then it has the largest uncertainty. In other words, it contains the largest information. It's intuitive, right? Because when your random variable is equally likely to be any possible sample, you are mostly uncertainty about this random variable. If your random variable is most likely to be, say, 1 or 2, I can guess that. I can guess, okay, it's 1 or 2. I have a quite large chance to get a correct guess, right? That means my uncertainty is relatively small. But if your random variable is equally distributed for all the samples, you have nothing. You have the least knowledge about what possible value your random variable takes. Then your uncertainty about that random variable reaches maximum. Assume that everybody knows that when the random variable follows the uniform distribution, is entropy becomes the largest, becomes the maximum, and you obtain the largest entropy. But I hope everybody will be able to divide this rather than just memorize the conclusion. Does it make sense? Any question?
So, what is the advantage of using entropy over variance? Why don't we just use variance?
You can use variance. If you want to use variance to determine the information or uncertainty of your random variable, is doable. To me, it's reasonable. You can imagine, like, okay, the larger the variance you have, the information, the more information your random variable contains, or the more uncertainty your random variable contains. That's totally reasonable to me. I just give you a most commonly used measurement that is based on entropy. You can define whatever you want. Any other question? Okay. So those are about the definition for discrete random variables, right? But we know that in many cases we are more interested in continuous random variables. So similarly, we want to define some entropy for continuous random variable. How can we do that? First, we want to inherit what we have observed, we have obtained so far for discrete random variables. Right? So we want to build up a connection from the continuous random variable to discrete random variables. How can we do that? We can do the discretization. We first try to discretize the continuous random variables into some discrete random variables. How can we do that? Suppose we're doing like one-dimensional, it's scalar. So we can partition the range of the continuous random variable into many small beans, right? And for simplicity, I just assume those these beans are of the same size, so their length is denoted by this delta. Right? And then I can define the corresponding random variable y, and y taking I if and only x falls in I B. Does it make sense? So these beans can be indexed, right? Can be indexed. Say this is the starting point of the fifth bean, so it is the left boundary. The position is say 5 delta, and the right boundary is 6 delta, and this right boundary is also the left boundary of the 6th bean, right? So this is 7 delta. So we can index it. So now we can try to compute the entropy for this discrete random variable. And how do we compute that? We know the probability that y taking I is equal to the probability that x falls in ith region. So which is the integral of your density over ith bean. So the starting position will be I delta, and ending position will be I plus 1 delta, right? So according to mean value theorem, right? This is from calculus, right? So mean value theorem just says that, okay, in this range, this integration, right? So let me just draw one example. Suppose this is the beam you want to integrate your density over. Right? So according to mean value theory, there exists some x inside this beam such that this area can be directly calculated as the density at xi multiplied with the length of the beam. So this is jump theory, just some theory, some result. So you can imagine that, okay, when I pick up some x, then I draw a rectangle like this, right? The area of this rectangle is the same as the area covered by the corresponding curve in this beam. This is the basic result. And now we can use this to calculate the entropy over the discrete random variable. Right? It's just a summation. You just sum over all the beans, right? Over all the beans means that your discrete random variable y taking 1, 2, 3, 4, 5, 6 until like infinity, whatever. And so this is pxi times delta is the probability that your discrete random variable y taking I, right? And this logarithm over pxi delta is a logarithm of p y equals y. And you, of course, you need to put a negative sign in front to calculate the entropy. So now, if we just do some simple manipulation, because logarithm of product, the length of beam multiplying with this probability, just this log summation, right? Logarithm of p of xi plus logarithm of delta. This is the logarithm of p of xi plus delta. And you just multiply pxi with this term and with this term separately, and you obtain these two terms. Is it clear to everybody? Everyone is comfortable here, right? And as to why this remains log delta, you can say because this term becomes this way. Because logarithm, because the summation over I pxi delta is just 1. And now we can try to shrink the size of beam. If you shrink the beam to be narrower, narrower, narrower until it approaches to 0, what happens? You can consider the limit of this summation as entropy for the continuous random variable, right? This is from our calculus, right? Try to refresh our mind with basic calculus. Right? So if you just squeeze your beam, right, it becomes very, very narrow until that there's only one single line in this beam. Then Pxi will be exactly at the boundary, right? Then this one becomes your entropy of the continuous random variable. But now let us look at whether this is feasible. Whether it's feasible to take this beam size to be approaching to 0. Right? So now let us take this limit, right? When
Why is minus logarithm of that and not plus?
You mean this part?
Yes.
This part?
Yeah. Why is minus?
Okay. Is it okay? Is this formula okay? Yeah. So this part is logarithm P of xi plus logarithm delta, right? The outside is multiplied with Pxi delta, right? And the summation or I and minus. Right? Now you multiply Pxi delta to logarithm P of xi, you get the first term, right? Now you multiply this part with this, you get a second term. The reason is that this logarithm of the delta is constant. You can move outside the summation, right? And then the other term is just the summation over I Pxi delta. This is actually the whole area covered by this probability density. It's 1.
So minus logarithm of that is not inside the summation.
Yeah, because it's an entropy, you need to take negative sign outside. So I hope you guys after the class try to follow this derivation again. You just need to get a sense. So now we want to make this beam to be smaller than this discretized. If you take the beam size to be 0, then your discrete random variable overlap with the continuous random variable. Then we can use that limit as our entropy, right? So we want to say whether it's feasible. If you take the limit that the beam size to be 0, we say there are 2 terms, right? So how about the second term? The size of beam when it goes to 0, logarithm of this beam size will be what? Negative infinity, right? And take negative again. This term becomes positive infinity. So it looks like it's not feasible. And now, why not just throw out this term? Let's just look at this term. And this term is what? If we take limit, right? First let us look at this one. If we take a limit over this summation, so we know when delta approaches to 0, then this one becomes Pxi, right? And this summation becomes integral. This definition of integral. So whenever you do the integral, conceptually, you can consider I first partition the region you want to integrate over into many, many small beams or regions, right? And you express them as summation. Then you just take the limit that when the size of region approaches to 0. So this is similar. This is the same thing. So now, if you take the size of beam to be 0, now it becomes an integral of Px logarithm of Px. And of course, I need to supplement with a negative sign outside. I get this form. Right? So when I get this form, I say, wow, it's quite consistent with the entropy definition for the discrete random variables, right? Except that I just replaced the summation with the integral. The other things are the same. And then we will choose this to measure the information or the uncertainty contained in the continuous random variable. This is called a differential entropy. It's not full entropy. But does it mean like this positive infinity term just meaningless? The answer is no. From coding theory, what does it say? It just means if you really want to code a continuous random variables, the length of your code will be infinite. That means you cannot 100 accurate code any continuous random variable. This is consistent with our practice, because in practice we always use like digital circuit, the digital computers, right? So what is digital computers? You discretize all kinds of continuous random variables. When you look at the computers, you always have it is 32 bits or 64 bits. So basically means that, okay, if your numerical number, the length of numerical number is over like 64 digits, we don't care. All the numbers with the same first 64 digits are considered as the same. Right? Same thing as in information theory. If you want to make a code, if you want to code something, you always first discretize the values you want to transmit. But we can still measure relatively which continuous random variable will contain more information or will be more uncertainty. Based on what? Based on this differential entropy. Does it make sense? Because this concept is so fundamental, I try to keep a slow speed to make everybody clear about that, right? Differential entropy can be negative. This is very different from the discrete case. So from discrete case, we know, okay, I have a probability vector, right? The density is a summation over all the elements in this probability vector. The summation is a logarithm of pi, and times pi, right? This will always be non-negative. Why? It's always be non-negative. Why?
Because the log crossovers are always negative.
Yeah. It's always negative. Right? And also we can prove it using like convex function like Jason's infinity. Right? And here one important piece I want to mention that. So somebody may argue that what if pi equals to 0, right? So in this case, it looks like the definition of entropy will be ill-posed, right? But actually, when pi equals to 0, you can still do this summation. So your term becomes 0 times 0, right? So in this case, we're not calculating this because this is meaningless. This is ill-posed. But we can replace it with a limit. So a limit when x approaches 0, x logarithm of x. Which is 0. To see this, you can use Robida law. If you take the limit, this will be logarithm x over 1 over x, right? And Robida's law tells you that if you take derivative on both the numerator and the denominator, and After that, take a limit. If the limit exists, then that will be our limit of the original form, right? You could take the derivative of both numerator and derivatives. So the numerator is 1 over x. The derivative, the denominator will minus 1 over x squared, right? So it is minus x. When x approaches to 0, this limit is 0. So clearly, this limit is 0. So that's why we replace 0 log 0 with limit. So going back to the continuous random variable, because differential entropy is not the true entropy. The true entropy is actually a positive infinity. You need to plus the positive infinity term. So that means when you calculate differential entropy, it is possible, it is quite possible that you get a negative value. Don't be surprised, don't scream. So actually you can take a look. If you have a very spiky Gaussian distribution, we'll calculate the entropy. We'll take the variance to be enough small, the differential entropy will be negative. You can look up the formula in Wikipedia and try to calculate a few values. So another interesting question. So suppose now I'm given a continuous random variable. I don't know the form of its distribution, but just to tell you, I know the expectation of x is some given value mu, and variance of this continuous random variable is sigma squared. Those are given a fixed. Now, can you find out a distribution for x such that its differential entropy is the largest? How can we do that? We can still turn it into an optimization problem, right? But we need to put extra constraints. First, your density must have its integral to be 1, right? And second, the expectation must be the given value mu, and variance must be the given value sigma squared, right? And then just add this Lagrange multiplier into the entropy. So this is the differential entropy. And lambda 1, lambda 2, lambda 3, the three terms represent the three constraints we just mentioned, right? If you solve this, you'll find that only when you have a Gaussian distribution, your differential entropy reaches maximum. That's an interesting question. I'll leave it as an exercise for you. So any questions so far? Irrespective of how to solve this optimization problem.
So what do you do when you see a negative? How do you interpret that?
You actually cannot interpret it. Because it's not true. It's not true entropy. The true entropy for continuous random variables is positive infinity. But we still want to compare which among a set of continuous random variables, which one is more informal, which one is not. Right? That's we come up the differential entropy. But differential entropy is actually not that meaningful to measure the information because it can take negative values. I'll give you a hint. To solve this optimization problem, you need to know a bit about function. You take derivative over function, we can solve this directly. But I think we won't cover the functional in this class. It's not required. So conditional entropy, right? Given the definition of entropy, naturally we want to like given the expectation, I want to calculate conditional expectation. Right? Given the joint probability, I want to calculate conditional probability. Same thing, right? So given x, the conditional entropy represents like given x, what is the information left for y? Right? So definition is like this. So it is expectation over the logarithm p y given x. So you can written as p y given x with respect to the joint probability of x y. And you can show that the entropy of the two random variables x, y can be written as the entropy of x only plus the conditional entropy of y given x. To memorize, I think it's much easier to memorize it because I can use one side to represent. So if you use circle to represent the information in the variables, two random variables contain, right? So we know the whole area covered by two circles are the total information contained, right? So now we can calculate this by what? So I can first calculate the entropy of x, which will be the area of the left circle, right? And then the remaining part will be the conditional entropy. So don't be confused, right? The overlapping part is not conditional entropy, because when I know x, I also know this part. This is nothing fresh, that's new. So the remaining things which are fresh or new to x is the conditional entropy. And probably the most important concept here, Kullback-Leibler divergence. So it is also called relative entropy. So Kullback-Leibler divergence is defined as a function over two probability distributions. So P and Q. P and Q can be the distributions for discrete random variables or continuous random variables. So you don't need to like look at this, just look at this. So the definition is the expectation of Px over logarithm of Px over Qx. So if you remove the negative sign, you actually need to switch the denominator and numerator, right? Px going upward, Qx going downward, we get expectation here. So from coding theory, it basically says, okay, if we use Q to transmit information for P, how much extra information do we need? And you don't necessarily understand this statement. Just know there's such kind of statement. We do not care about it. What we care is that first, PR divergence is always non-negative. And KL divergence is widely used to measure the difference, or in other words, similarity between two distributions. That's very, very important. Why? Because consider that if I want to do Bayesian inference, right? So in many cases, the true posterior is not feasible to compute. I want to find a best approximation from some family of distribution, right? How do I define best? How do I define best? I want to find someone which is closest to the true posterior, right? And I need to define what is closeness. KL divergence is one measure. That's why KL divergence is so important. And KL divergence has very nice properties that it is always non-negative. And it is easy to prove that. I will leave it as an exercise. Does it make sense? Or do I need to prove here? Just give you a hint, right? So remember the KL divergence between P and Q is expectation over P over Q, right? So if you take negative sign out, so it becomes expectation of minus logarithm Q over P, right? It's the same, just switch the denominator and numerator. So remember, minus logarithm is convex. Because logarithm is like this, right? It's concave. If you take minus of the logarithm, it's convex. And now you can use just so you switch the expectation and the function operator, you get a low bound. So that means if you first show the expectation of P over Q over P, and then take negative logarithm. The remaining is that what is the expectation of Q over P with respect to P? What is it? I heard that. 1, right? If you're not clear, just write it down. So it's a Q x over P x, and this is something we want to take expectation, right? So it should multiply with Px because it's with respect to Px, and over Px, right? So you know, okay, Px will cancel, right? So you integral over Qx only. So Q is a distribution as well, so your integral is 1. So this is 1. You take logarithm over 1 is 0. That's why PR divergence is always guaranteed to be non-negative. And you can show that when if and only if P and Q are exactly the same, 0, 0. But be careful, PR divergence is not distance. The reason is that it's not symmetric, it's asymmetric. The KL divergence between P and Q usually is not equal to KL divergence between Q and P. So that raises an interesting question. If I do the approximate inference, which value should I choose? Should I choose this one or should I choose this one? Right? The answer is there's no answer. You can choose whichever you want. And there is a more general definition of the divergence, which can also measure the similarity or closeness between two distributions, called alpha divergence. Alpha divergence. So alpha divergence, on the alpha divergence definition, the divergence is determined by the choice of alpha. It turns out that when alpha takes to 1, it becomes one particular KL for a particular order. If you take alpha to be another value, you switch the order. And you can also take other values of alpha. So there's the so-called like the general alpha divergence versus inference or whatever. And anyway, when we discuss the approximate inference, we'll come back to this later. And mutual information. So mutual information actually measures how many information two random variables share. So remember the diagrams we just draw. If I have two random variables, those circles represent information it contains, right? So the mutual information actually is the overlapping part. This is the mutual information. And this part is what? Conditional entropy, right? So this part will be given x. And this part will be x given y. And this is the definition of mutual information. So basically, it is the expectation xy over this logarithm drawn probability over, yeah, it's correct, over the marginal probability of x, y. And you can also show that the mutual information is equal to hx, the entropy of x, minus the conditional entropy, and entropy of y minus conditional entropy of y given x. and I link the proof as access for you. So so far we have reviewed those key concepts in information theory. It's not too much, but those are so fundamental, and whenever we talk about those concepts, you should have like instinct about the meaning, the properties in your mind. Right? So what is entropy? What is the definition of entropy? And what is differential entropy? How is differential entropy derived? Right? What's the difference between differential entropy and entropy? And entropy is an indicator for uncertainty. Because Bayesian inference or Bayesian modeling at work is advantageous in terms of uncertainty quantification, right? So entropy obviously is a good indicator. And KL divergence and its properties. KL divergence is used to measure the distance or the similarity between two distributions, but it does not mean it's a rigorous distance because it's not symmetric. And mutual information, the information shared by two random variables. Of course, we can calculate the mutual information among 3 random variables, 4 random variables, etc. Any questions so far? Okay, so in the remaining about 10 minutes, let us start with another topic, conjugate R and the exponential family. This is also a key component in probabilistic modeling. So not like the previous boring part when we quickly go through those common use distributions everybody knows. So hope right now I will slow down and make sure those important parts I can emphasize. Okay. So basically we'll first review Bayes' rule and point out or emphasize again why it's so hard to compute posterior distribution. And then because of this computational intractability, people find out a class of very easy to compute prior. Likely it leads to the concept of conjugate prior. And then we give the commonly used examples. Actually, you have already seen that, but here I want to reinforce again. And then we'll introduce exponential family. And what are the properties of exponential family, and what are the conjugate prior in general for exponential family. So we have a reviewed maximum likelihood estimation and map estimation, which only give one estimation of the parameters, which obviously is not our goal for Bayesian inference, because we always want to calculate the posterior distribution over the parameters given data. It's a distribution, it's not a point, right? And how can we do that? We can use Bayes' rule. Right? This is kind of truth, right? It's something always stay on the ground to support the whole area. It's a Bayes' rule, right? But to calculate the posterior distribution according to Bayes' rule is not easy, because you need to calculate this marginal distribution over the data set, right? This marginal distribution, you need to calculate the marginalization over the joint distribution, right? So you need to integrate out the random variables data here. And in most cases, this won't be feasible to compute. I can give you one example. It's not necessary to be like high dimensional. Just one single function, the logistic function, which is in your homework, right? So suppose I give a theta, which is say beta distribution, whatever, right? And now my observation is binary. It's just a logistic function, which is 1 over exp minus theta to the let me write down this to the 2y minus 2 theta. This is a valid likelihood. don't need to, you can check after, right? So if y equals to 1, then this is just a logistic function. If y equals to 0, it becomes 1 minus logistic function. So you can recheck, double check after the class, right? So this is a likelihood. So now if I want to integrate out there, if I want to integrate this to get the probability of the beta, which is P of y. Usually, whatever data you choose, it's very hard to calculate this integral. This is just for one-dimensional case. For one-dimensional case, I have a lot of such kind of examples. So you can imagine if I have a high-dimensional case, how hard is it, right? So at the early stage of Bayesian statistics, people found out it's so hard to compute the posterior distribution. But sometimes I still want the posterior distributions to analyze. What should we do? Right? People find out a class of the special cases such that this posterior distribution is very easy to compute and is analytical. This class of cases is called conjugate Farr and conjugate distributions. So what is conjugate Farr? Here's the definition. It's kind of messy, but the idea is quite simple. So if we are given a Farr distribution, and a likelihood function, right? If the corresponding posterior distribution, which is calculated follows Bayes' rule, has the same function form as the Farr, then we say this Farr is conjugate to the likelihood. So if your Farr has some special form and you're given a likelihood, right? You'll use this Bayes' rule to calculate posterior. And it turns out the posterior has exactly the same form as the Farr, but with different parameters. Then we say, okay, this Farr is conjugate to likelihood. So the conjugation or conjugate distribution, this kind of things, is not for one element, it's for two elements. It builds up a relationship between the Farr and likelihood. So we say a distribution or Farr is conjugate, must say is conjugate to what? To give you a concrete example, beta Farr is conjugate to Bernoulli likelihood. To see this point, so suppose we first sample a general sample from the beta Farr. Right? This is a beta distribution, so we know the beta distribution is sample is a probability between 0 and 1. Right? This sample from beta distribution is density followed this way. So the Farr is determined by A and B, right? And density is proportional to mu to the A minus 1 minus mu to the power of B minus 1. Right? This is something we mentioned in our last lecture. Right? And then suppose the likelihood is Bernoulli. So that means x is either 0 or 1. So the Bernoulli likelihood will be like this. The probability of your binary observation is mu to the x times 1 minus mu to the power of 1 minus x. Right? Now, let us combine this Farr and likelihood and follow the Bayes' rule to calculate posterior. We know the posterior is proportional to the product of the Farr and the likelihood. Right? So let us try to multiply them together. Right? We can first just forget about those normalization constant. We just merge the terms regarding mu, right? Because we want to calculate posterior of mu given observation x. Right? So when we merge terms of the regarding mu, we found out okay, we can merge the terms with mu as the same base, right? So we can just add some the exponent, which is x minus a plus x minus 1, right? Similarly, we merge all the terms with 1 minus mu as the base. So it becomes b plus 1 minus x minus 1, right? So no, we know that posterior distribution is proportional to this mu to some exponent, multiplying 1 minus mu to some exponent. So what do we conclude right now? function form, they take the same form as the prior, right? The only difference is exponent. For the prior, the exponent will be a and b, right? And for the posterior, the exponent will be a plus x and b plus 1 minus x, right? So it's actually the posterior follows the beta distribution again. And this posterior distribution is parameterized by a plus x and b plus 1 minus x. That's why we can claim that the beta prior is conjugate to the Bernoulli likelihood. Because after we calculate the posterior distribution, they have the same form but parameterized by other things. So here's one example. Right? So suppose our prior is parameterized by 2, 2. A is 2 and b equals to 2, right? So we say it's kind of balanced. So mu, the chance that mu is less than 0.5, bigger than 0.5 are equal, right? So now suppose we observe x equals being 1, right? That means I just observe 1. So the likelihood will be just mu. If you calculate likelihood in terms of function mu, it's just a log. Because mu to x 1 minus mu to the power of 1 minus x will just be mu, right? So it's just a line. And then you just combine it together, you calculate the posterior distribution, which is also beta distribution. It now becomes beta mu 3, 2, right? Remember, the posterior is a plus x, b plus 1 minus x, right? So x is 1, a is 2, so now this becomes 3, and 1 minus x is 0, right? And here it's still 2, right? So now we can see the shape of the posterior distribution density changes, right? It bias toward to 1. That means after I have observed x taking 1, I believe that mu is more likely to be bigger than 0.5. Any question? Okay, let us stop here, and we will continue on Thursday.